So today we are starting dynamic programming, which is arguably the most important technique that we will cover, and one of the definitely most important techniques for, guys, please be quiet, for algorithm design. So maybe we should start with an example. So assume that you are running a small car factory, okay? And you have only two production lines, right? And they both have stations that do the same task, but over time the equipment was not purchased at the same time, so it might be the case that on the second production line for this particular stage of assembly, this station can do faster job than maybe older piece of equipment on the first production line, and vice versa. Of course, if you want to speed things up, you might want to finish Kate's task here and then take the partly finished product across the production lines and finish the Kate task here. But of course you then incur some delay depending on how much time it takes to switch from one line to the other line. And then one day a very rich sheikh comes to your factory and wants to get his Rolls-Royce as soon as possible. So what you want to determine is how you should assemble it. So it takes a certain amount of time to get the whole process started, to put the chassis either on production line 1 or some other amount of time, E2, to the other production line. And then you want to see where each particular task should be done. Maybe the fastest way is to do on the first task on the second line, then to transfer to the first line and do second task there, then get it back to the second production line and do the task there, and then maybe again change and so forth. And so what you have to determine is what is the fastest way to get this Rolls-Royce all finished. So how many different paths through the factory are there? If just all possible paths that you can take in assembling this car, how many of them? 2 to the power of n, right? Because you can think of each path as encoding a binary number, and if it's 1, it's say it's this stage is done on the first line, and if it's 0, then it's done on the second task. So if you would to do it brute force, you would have to examine 2 to the n many different paths, right? And that's prohibitively expensive. It's an exponential time. Okay, so we want to find a method that works faster. So let me ask you the following question. So what we are going to do is you see that this is now the standard theme of dynamic programming. Dynamic programming simplifies things by making them more complicated. Okay? So what is the idea? The idea is to generalize the problem and actually solve more problems than you are asked to, but to trade off this apparent increase in in generality with producing extremely simple recursion between optimal solutions. So, for example, if so in this case, how we will generalize the problem is we are going to find optimal path through the factory that has the property that it finishes with one particular stage K to be done at the, say, second line. And another problem that will be, again, finding optimal path through the factory, but the K task is done, or maybe I should point here, the K task is done on the first place. Okay, so say we are now considering just optimal solution to make it to complete the K task here on the first line. If you now consider the restriction of the path, say up to whatever, say, stage of assembly was, do you think that this restricted path would be optimal solution to the problem of finding the fastest way through the part of the factory with with end stage done here? Right, so if you have this is a K stage, right? And you have two assembly lines, and say I am considering, and this is the end stage, and assume that that this is the optimal path, the fastest way through the factory from the very beginning to the K stage of assembly, so that that stage is done on the first assembly line. And if I truncate this optimal path up to, say, this point, is it the case that the remainder of this path is the optimal trajectory through the factory that ends with this point here? Does this have to be so? Well, assume that it is not, but that there is a better way that goes in some other way to this point. Would then this be an optimal path through the factory that ends at this stage here? No, because you can do cut and paste algorithm, right? You can simply replace this piece of the path with the better one and end up with something that is overall faster solution for this extended problem. So what do we have then? We have a particularly simple recursion. So what we are looking for is the shortest possible time to finish the kth task. So all the tasks from 1 to kth task on assembly line 1, right? What will this be? Well, this would be the task, the optimal time to finish the K minus first task on the assembly line 1, plus the time to finish the K task, right? So let me see if, unfortunately I forgot my laser pointer. Oh, umbrella. Okay, so you see, this here is the optimal way to end to this point, plus just finishing the kth task here, right? And so it will be mean of this and this value here, which is the optimal way to finish the K minus first task here, then transport to the to the first line, right, from the second line to the first line, and then finish the k task here. So optimal solution must be optimal, the better of the optimal way to get up to here, plus just time to finish the k task here, and optimal way to get through the k minus first task on the second line, plus the time to transport it to the first line and then finish it off here, right? And then we have the same equation for the optimal way to finish the k task here, which is simply the optimal way to finish the k task here, plus the time to finish, k minus first task here, and then k times here. And the mean of that, and the optimal way to actually finish it here, and then transport the partly finished product to the second line and finish it here. Right? So notice, so these are kind of two intertwined recursions that run in parallel, right? But the important thing is that you see, you don't repeat the work, because the optimal solution for k up to kth task, either on the first and on the second line, is obtained simply from optimal solutions for task up to k minus 1, either on the first or on the second line, plus the overhead, what you extra work you have to do. In both cases is finishing the kth task, but in this case, when you are changing the assembly lines, you also incur this T2, right? And then finally, what you have to do is simply you will get optimal solution to get up to here, optimal solution to get up to here. To this optimal solution, you add price x1 to move from the first assembly line to the storage, and here optimal solution up to here, plus the cost to move to the storage from assembly line 1, and you take the smaller of the two, right? So we didn't, instead of solving simply the problem, what is the shortest way to get to the production line, we solve two and many problems. Namely, for every k, we find optimal solution to go through the factory and finish the kth task here, as well as optimal solution to get through the factory in such a way as to finish the kth task in the assembly line 2. Why do we do that? Because while we are multiplying the kind of number of problems we have to do, instead of just one, we find optimal solutions for every k. So we have 2k problems, but the benefit is that the recursions that link optimal solutions for k minus 1 and optimal solutions for k are very simple. And so this is really the best way how to think about dynamic programming. You generalize your problem in such a way that the solution to sub-problems allow very simple recursion. And in order to be able to do that, we have to have optimal sub-problem property. You see, so what do I mean by that? If this is my optimal trajectory so that I finish the task here, and then I truncate it up to this point, the truncation will be also optimal solution for the trajectory that ends with that point. Why? Well, if there was something better going some other way, then this solution wouldn't be optimal because I could simply check out the tail here and replace it with a better way to come here. So in this way, optimal solutions for the subsequent stages are built from optimal solutions of the smaller problems. Okay. Let's see another example, namely matrix multiplication. Well, you know from linear algebra that if you have three matrices that are size compatible, right, then you can multiply them either as first multiplying A and B and then multiply by C, or you first multiply B and C and then multiply that with A. So matrix multiplication is associative, right? In general, it's not commutative, but for compatible matrices, the ordering in which you multiply them does not matter as a result, right? However, it can hugely matter in terms of the workload, in terms of the complexity of the algorithm. Why? Well, here is an example. So you have one matrix that is 10 by 100. Then you have another skinny matrix 100 by 5, and then a matrix 5 by 50. So if you multiply first matrices A and B, then the result, of course, inherits the height of the first matrix and the width of the second matrix. So AB, the product AB will be just 10 by 5. And then you multiply it with 5 times 50 matrix. The other way of doing it is you first multiply these two matrices, right? And then you multiply with the matrix A. But notice how vastly different this is, because if you multiply a skinny matrix with a long matrix, then the product, of course, inherits the height of the first matrix and the width of the second matrix, so you get a large matrix 100 by 50. So how many multiplications do we need? So here, so for each entry of the result, we have 100 multiplications, right? So, and the matrix is of size 10 times 5. So we have 50 entries, right? And for each entry here, we have to do 100 multiplications in order to multiply a row here with a column here. So this is this factor here, 10 times 5 times 100. And for the second multiplication, you have to multiply for each entry just 5 terms, because the width here is 5 and here the height is 5. So you have 5 multiplications, and the size is, of course, 10 times 50. So here we get, what do we get? 5,000 multiplications plus 2,500 is 7,500 multiplications. Now let's see how many multiplications we have to do if we first compute B times C. Well, if you compute B times C first, then here you have 10 times, did I mess up something here? It is 10 times, sorry, I'm just looking, this is where the multiplication took place. So it will be 5 times and then 100 times 50, right? And for the final step, when you multiply these two, this is, so what is the dimension? 10 times 50 and 10 times 100, right? 10 times 50 times 100. And this is 25,000 plus 50,000, which is 10 times as much. 10 times as many multiplications than what you would have to do if you did it first multiplying A, B, and then C. Okay? Yes, any questions? So, while the product is numerically exactly the same, the sum total of how many multiplications you have to do, it can be vastly different. So now, we want to solve the following problem. Assume that rather than just 3, you have a sequence of matrices, A1, A2, up to AN. And your task is to group them in such a way as to minimize the total number of multiplications needed to find the product matrix. So, how many different placements of parentheses are there? You see, if you consider, if you want to recurse, this is essentially in how many ways you can parenthesize the product of matrices to get a different tree that corresponds to the term, right? So you simply look now where is the principal operation. And the principal operation can be anywhere, say, having I matrices on the left and n minus I matrices of the right. And placements in the first group of I matrices is independent of the placement of parentheses in the second group. So you have to sum, and you can, of course, break this in any possible way. So this is... let me just quickly. So you have so this is AI, and then here is up to AN, and so we decided to place the first to be up to AI. So here will be A1 up to AI, and then here we have AI plus 1 up to AN. So the possible ways to parenthesize this principal operation can be anywhere here between any two of the matrices. So you have n minus 1 choices for I, and once you decide where you break this chain, the total number of parenthesizing this term here is independent from how you do the parentheses here. So the total number will be product of how many ways you can do it here times how many ways you do it here, and then you have to sum through all possible i's. So you get this recurrence, and these numbers are called Catalan numbers. And it's easy to see that they grow, in fact, faster than 2 to the end. Okay? So if you were to try by brute force placing all the matrices, all the parentheses in any way, this would be just prohibitively slow, right? So we have to do this in a better way, right? And what is the idea? Well, the idea is that when you consider all possible placements of parentheses, then for, say, if I break up to AI minus 1, and then consider sub-problems here, some of the sub-problems will be repeated. So the idea is to do this exhaustive search, but without repeating already calculated optimal solutions. So the idea is then to consider the following generalization. So all we care is what is the optimal placement of parentheses for the n terms. But this is hard to tell directly, so instead we generalize the following. We find optimal placement of parentheses for any substring of the matrices from matrix AI up to matrix IJ. Yeah? Why are we doing that? Well, because then the computing the total number of placements, computing the product, computing the placement of parentheses so that the product is minimal is very easy to recurse. Why is this so? Well, what is the minimal number of multiplications needed to evaluate the product between matrix AI to matrix AJ? Well, this will be, you see, this is min over k. What we now do is we search through all possible placements. So here is now AI, and here is IJ, and somewhere here in between is AK. Okay? So now we are simply going through all possible places where to put the principal operation, the last multiplication. And this can be done by splitting the whole chain in the following way. AI, and then the product of all of them. And then AI plus 1, and then the product of all the remaining, and so forth. So you simply search through all possible k, and you now recursively compute this value by simply summing up the number of multiplications needed to multiply first matrices from AI to AK, and then to plus the total number of multiplications needed to multiply matrices from AK plus 1 to J, plus, what is this here? This is simply the price to multiply the result of the resulting matrix by taking first k of them times the matrix to take the remaining k plus 1 up to ij. What is the format of these two matrices? Well, it will inherit the height of AI, right? So it will be just size I minus 1, right? Then times it will be the resulting format, right, will be just the height of, the width here, right? So you have the three, this propagates from the right, this propagates from the left, and k depends on the place where you broke the, your chain off, right? So now notice that why is this a correct recursion? How would you order these chains? It's enough just to group them according to their length, right? So this is actually a linear recursion. So you will build a table. You will build a table that looks as follows. In this row here, you will have all the products of the form A, say, I plus 1, all the way up to A, say, I plus k minus 1, right? Because this is k matrices. So for all possible starting points, you will find all the products that contain k matrices, and then recursion is correct because no matter where I break the chain from AI to AJ, if I break it on, say, position K, then K minus I is clearly shorter than J minus I. So this and that, depending on the size, is already computed previously and placed in our table, right? So this makes it a correct recursion. So notice this looked deceitfully, so sometimes students ask me what's the difference between dynamic programming and doing it by brute force. Well, brute force will take exponential amount of time, and the reason why it takes exponential amount of time is that product of many smaller subchains is done many times because it appears in a great number of different ways to put the parentheses, right? So, however, in this way, the total number of multiplications is computed from previously evaluated optimal number of multiplications to multiply matrices from I to K, and then from K plus 1 to J, plus the price. If you see, this is precisely the how many multiplications you have to do to multiply this product by that product, right? For each entry, the format is Si minus 1 Sj, and Sk, namely the height of the Kate matrix, is precisely tells you, or which is of course the same as the width of the K minus first matrix. So this simply gives you the price for the last step of the multiplication. So it is exhaustive search over all possible breaking points for the chain, but for each subchain, the multiplication is done only once and placed in the table. And this is what gives dynamic programming its efficiency. Okay, so let us now look at another example. You remember when there was this scare about bird flu, right? Well, people suspected that this bird flu is actually related to the Spanish flu that I think in 1915 killed a large number of people, I think in tens of millions. So somehow, how do you, of course viruses mutate fast, right? So how do you tell whether two viruses are related to each other? You tell by similarity of the sequences, right? But there can be some additional base pairs in one of them, and some of them can be deleted. So then the problem was where to find the virus from 1905, 1915. So guess where did they find it? What country did they go to?
Russia?
Russia would work, but they didn't go there. They went to Canada. Where in Canada? All the way as north as possible, because corpses simply don't decompose there at all. They simply get frozen. So they got lung tissue from the victims of this Spanish flu, and then what they had to do is, one of the measurements for similarity of these two sequences is to find the longest common subsequence. So what is the longest common subsequence? It's you simply, from both of them, you can delete some of the bases. and what is left should be identical, and it should be as long as possible, right? Because this would indicate that these two viruses are closely related, while some new material might have been added and some of the base pairs lost. If you remove whatever has been added lately, and from here, from the other one, you remove whatever was lost right in time, and here whatever was added later, they should end up with you should end up with a pretty long sequence that is identical subsequence for both of the two. So the problem is how do we find the longest common subsequence? How do we do that? You see, if you, instead of solving this problem, we are again generalizing. So instead of solving this problem, we will do the following. Say if the size of the sequences is n times n, we will find the longest common subsequences for all sequences starting from the very first, from C0 up to Ci, and how did I call the other one? So this is S, S0 to Si, and S star 0 to J. Okay? So notice is instead of solving one problem, we are now solving m times n many problems. Right? So quadratic number of problems. But if you do that, then the recursion is extraordinarily simple, right? You have two cases. First case is that the ith base in the first sequence and jth base in the second sequence are equal. This means that the longest common subsequence will be whatever is the longest common subsequence of the sequences C for the sequences up to I minus 1 and j minus 1. Oops, here it should be plus 1. I'm sorry, I have to correct the slide. So it's